This is a brief video to help you understand how to generate fault trees. So a fault tree is a graphical structure that creates a logical relationship between components of a system and helps you organize the threats to those components that would disable the system. It's important to note that it is quite possible to calculate probabilities and propagate them up through the fault tree, but we are not going to do much of that. This is a widely used methodology to understand system failures, and it's an adaptable framework for analyzing failures. So let's begin with a slide from NASA. They use fault trees to evaluate all of their launch vehicles and many of their processes, and the basic fault tree structure is outlined here, where the top event is the undesired event. You don't want this thing to occur. I think of this as a system failure. And then there are intermediate level events that can cause the system to failure, and you want to propagate those down to basic component level events that can lead to the intermediate failures, which can lead to the overall system failure. So let's just take an example. I presented this in the in-class lectures before. If we had a nuclear power plant, of course, this is not an exhaustive or an extensive fault tree. I'm just trying to illustrate the process here. We would have failure of the nuclear power plant under two conditions. One is we have station blackout, which means we have absolutely no serviceable power to the systems in the power plant, or if we lost all the coolant water. Coolant water is important to keep the core from overheating. And so how would you get these things to occur? Well, you could lose your coolant water if you lost your water supply or if station blackout occurred. So it's interesting, you'll note that we have this top level event, which is the thing we don't want to occur, nuclear plant failure. And that can happen by either station blackout or a loss of coolant water. So this logic gate in here is important. And then if we drill down into station blackout, we only lose serviceable power to the plant if we lose our connection to the grid, we lose our backup generators, and we lose our battery backup systems. So station blackout only occurs if all three of these basic events occur. That's a very unlikely scenario. So an AND gate requires multiple things to occur. In fact, it represents redundancy, while an OR gate means either this can happen or that can happen. So we'll talk a little bit more about that in a moment. But we can always add detail. We talked about the station blackout branch of the tree, and that could only occur if we lost grid, diesel, and battery backups. But if we look at grid power failure, we could lose transformers that connect us to the grid, or we can lose transmission lines. And how might we lose transmission lines? Well, we could lose the transmission lines through a weather-related event, an overload event, which would cause melting, or an accident that actually knocked a tower down and brought transmission lines down with it. There are lots of things that can happen to bring down the transmission line. And so you drill down from station blackout to one of the basic events, and then you get into more detail below that. The other thing that's important is AND gates represent redundancy, and the probability above the AND gate is lower than the probability of any one event below the AND gate. So this is just an illustration. These are not real probabilities. I'm just trying to show how these probabilities get propagated up through the AND gate. If the probability of grid failure was 1%, diesel failure was 1%, and battery backup was 1%, 1 in 100 is a pretty high failure rate, and we are not going to want that for these systems. But nonetheless, the way you propagate those probabilities up through to generate station blackout is you multiply each of them together. And if you do that, you see that we have 0.0001%. So we had 1% down here, and we ended up with a much lower probability. And the lower probability is because all three of these things have to occur in order for us to suffer station blackout. Those are redundancies, and so they lower the probability. You get the probability above the AND gate by multiplying the probabilities of the events below the AND. If the top level event was connected by an OR gate, meaning that this thing would occur if event 1 occurred, or event 2, or event 3 occurred, and you propagate those probabilities up through the OR gate, it turns out that events connected by OR gates, the top level event is going to have a greater probability than any of the individual event probability. And so if we had a probability of failure of 1 in 100 for event 1, 2 in 100 for event 2, and 4 in 100 for event 3, we determine the overall top-level event probability by taking the product of the reliabilities, which is 1 minus the probability of failure, for each of the lower-level events. We multiply those together, and we subtract that from 1, and it gives us an overall probability of 0.069, almost 7 in 100. So you see that that probability is higher than the probabilities of any of these events down here. So OR gates are not good things to have in systems that are critical. Now, it turns out we do have them, and you can appreciate how the probabilities propagate up and what sort of quality control you would have to have on the lower level components that occurred in the fault tree. So this is an example that I talked about in class of an insulin pump. You administer the incorrect dose if you didn't measure the sugar level correctly, you delivered the dose at the wrong time, or you had a delivery system failure. And so the probability of this event up here above the OR occurring is going to be higher than the probability of any one of the events down here that are connected into that OR gate. Well, each of those events, incorrect sugar level measurement, well, it turns out that could occur if we had a sensor failure or if we computed incorrectly. And we could compute incorrectly if we had an arithmetic error somewhere or an algorithm error. The equation that we used was incorrect. So you propagate these base level events up through the higher level events all the way to failure of the thing you're most concerned about. And you connect them with logic gates that appropriately relate the lower level events to the higher level event. So airplanes are systems of systems. We talked about this as well. There's propulsion system, the avionics, the fuel, the landing, communication, passenger, and the one that everyone has heard about recently in the 737 MAX is the maneuvering characteristics augmentation system. Now I'm just going to draw a simple engaged nose down override. There's a software program that looks at the airspeed and the angle of attack. And if the airspeed is too low for the given angle of attack, then the MCAS system automatically lowers the nose. So it drops the nose down so that the angle of attack is not so high. In order for that to engage, you have to have airspeed too low and the angle of attack too high. And the angle of attack too high, you really want redundant sensors so that you're connecting all of these through AND gates, so that the probability of the bad event up here, an engaged nose down override when it didn't warrant it, is going to be much lower than the probability of anything going bad down below in the tree. So in the angle of attack, if you have two sensors that are measuring the angle of attack, you're going to require both of those sensors to report an angle of attack that's too high, and both of the airspeed indicators to indicate an airspeed that's too low for that given angle of attack, and then you would engage the nose down override. So if we were to look at a water treatment plant and we wanted to understand, okay, what could cause the delivery of potable water to failure? So you have all of these customers down here, and you're providing those customers with potable water. You get that potable water from a source. It could be a lake, it could be a river, it could be an underground aquifer. You got to get that water from that lake through a treatment system and into a storage tower to regulate pressure, and then out to all of the customers. So this is showing an elevated water storage tower and then a backup reservoir at ground level. But nonetheless, there are lots of things in this system that would have to go wrong in order for you to stop delivering potable water to the customers. And so a rudimentary fault tree for this could be something like so. The top level event that we don't want to occur is no potable water available to the customers. The only way that could occur is if our supply has been compromised or we're not able to deliver from the supply to the customers. So how could the supply be compromised? Well, in order for the supply to be compromised, the source would have to be compromised and the storage that we had would have to be compromised. So both of those things have to occur in order for us to lose our supply to the customer. But we could still have some delivery issues, and we could have trouble delivering to the customers if we couldn't treat the water properly, or the pipes had failed, or the pumping systems had failed. So these are logically connected through OR gates here. These two are connected through an OR gate, and the supply is connected through an AND gate. So you can see how we could suffer treatment failure if the workforce was compromised, or we had no power to the treatment plant, or we couldn't deliver chemicals that are required to the treatment plant. These are just a few of the possibilities. The pipes could go bad if they had corroded like they did in Flint, Michigan, or they actually corroded all the way through and leaked so that you lost your water pressure. Or there could be a construction accident or some other kind of accident. The pumps could fail either mechanically, or we could lose power to those pumps. So you can see how you build out the system. You have the event, the top level event you care about, and the lower level events that can lead to failure, and then the basic things that propagate up through the fault tree to create the high level event failure.